Okay, we last finished looking at monosubstituted cyclohexanes, and now we're going to get into a disubstituted cyclohexane. And if we have multiple substituents on our ring, we have to use wedges or dashes in order to let the viewer know whether a group is pointing up towards the viewer or going down away from the viewer. So if we look at this cyclohexane right here, we see that since the chlorine is on a wedge, we know that it's pointing up towards us. Now, that up, it could be up and axial, and it could be up and equatorial. And you see that we have the two conformations right here. These are going to be in equilibrium with each other, these two conformations. And you see that in one of them, the chlorine is up and axial, and in the other one, it is up and equatorial. The same thing would apply for the methyl group. If the methyl group is going down, okay, because it's on a dash, well, here it's going down and axial because we know that axial and going up and axial and down and axial alternate. So that means that here it's going down, but it's down and equatorial. So down and equatorial, like that. So realize that the chlorine is up in both chair conformations and it's down in both conformations. But again, we can have up and axial or up and equatorial. We can also have down and axial and down and equatorial. Now, next thing is I'm going to label these two conformations as A. So we'll call this one A, and we'll call this one B. If I have an equilibrium between A and B, could anybody tell me, would the equilibrium lie to the side of A or B, do you think? Which side do you think the equilibrium would lie to? So it should lie to the side of B. It should lie heavily to the side of B. And the reason why it's going to lie mostly to the side of B is that, remember, in here we have these 1,3 diaxial interactions between the groups that are equatorial and the hydrogen, or sorry, axial, and the hydrogens that are axial, right? We have these steric repulsions between the methyl groups and these hydrogens and the chlorine and these hydrogens. Whereas in B, where the two substituents are both equatorial, we don't have any of those 1,3 diaxial interactions. And so B is going to exist, or is going to predominate at equilibrium. Let's see here. It says, draw both chair conformations for the following molecule. Which one is more stable? So first thing we'll do is we'll draw the two chairs. And first we'll draw one where the carbon is, where there's a carbon going up and to the right. So we'll draw one that looks like this. So like this. And then we'll draw one where the carbon is going up and to the left. So that's not very pretty. Maybe something more like this. Okay, so like this. Like this. And this. Okay, so those are my two chairs. That's my best drawing. And of course, these are going to be in equilibrium with each other. Now, let's slow down here for a second. The way that our book likes to do it is he kind of always starts with the chair where the carbon is in the top right. So I'm going to move that one over here, and I'll put this one, I'm going to put this chair, I'll put this one over here, because this is just kind of the way that David Klein does it in the solutions manual. And I want to try to be somewhat consistent with your solutions manual. So we'll kind of start like this. Another thing is that whenever he draws a cyclohexane, I think 99% of the time, whichever carbon is at the top, that's going to be this carbon. And then when you flip the ring, it's going to be this carbon. Okay, so you flip the ring, right? And this is coming down like this. All right. And so if we have one, and then we have two, and then we have three carbons, and we're going clockwise around the ring, that would mean the blue carbon would be this one or this one, right? And the yellow carbon, of course, would be this one or this one. Okay, so let's start with the ethyl group. Let's imagine that the ethyl group is up and axial. And it doesn't matter. It could be up and equatorial. It could be up and axial. That doesn't matter. But let's just start with it as being up and axial. So up and axial. So let's just imagine that. If we have our ethyl group going up and axial on the first one, it's going to be like this. So if it's up and axial, that means that when we flip the ring, it's still going to be pointing up, but now it's not going to be axial, it's going to be up and equatorial. So it's still pointing up, but now it's going to be up and equatorial. So what's up and equatorial going to look like? Well, remember that our bond coming off that's equatorial has to be parallel with those two lines. So our bond is going to look something like this, and we're going to have our ethyl group here. Again, this is up and axial. This is up and equatorial. Okay, so I have a question for all of you. If I put, if I just show this hydrogen that's pointing up here, like this, okay, if the ethyl group is up, if this is up and axial, what would this up be? Would this be up and axial or up and equatorial for this hydrogen? That be up and axial or up and equatorial? Exactly, it's going to be up and equatorial because we know that up alternates. Up and axial, up and equatorial, up and axial, up and equatorial. So if the hydrogen is on a wedge, that means it's coming up, so it's going to be up and equatorial. So that means that this is going to be up and equatorial. And that means that the other hydrogen, the one that's going down, let me use my black pen. Here we go. That means that the one is going down. Since every carbon has one axial and one equatorial group, that means that this hydrogen is going to be going down, down, and axial. So up and equatorial and down and axial. Okay, well, if they alternate, right? So if this hydrogen that's going down is axial, that means that the methyl group here is going down. And since axial and equatorial alternate, that means that this must be down, down, and equatorial. So now when I go back here, since this is up and axial in this conformation, that means that this has to be down and equatorial. So I'm going to draw my bond to my methyl group as going down and equatorial, right? It's parallel to these two lines, right? Let me highlight them for you, right? The bond has to be parallel to those two lines. And there is my methyl group. So let's put in the methyl group like that. Is everybody with me on how I went from here to this first chair? Any questions about that? So if the ethyl group is up and axial, that means the methyl group has to be down and equatorial. Okay, so now when we flip the ring, the ethyl's still going to be going up, but now it's up and equatorial, and my methyl group is going to be down, but it's going to be down and axial. So I'm going to put my methyl group going down like this. Now it asks me, which one of these conformations is the most stable? If I call this one, let's call this one number 1, and we'll call this one number 2. Could anybody tell me which one of these conformations would be the most stable? Keep in mind, an ethyl group is bigger than a methyl group. Yes, thanks, Clinton. It's going to be number 2. It's going to be the more stable. So the equilibrium is going to lie to the side of the second one. So if I draw my equilibrium arrows, excuse me, I have a big one pointing towards the one on the right and a little one pointing towards the one on the left. Why is this one going to be more stable? More stable because the larger group is in the equatorial position. Here we have the larger group in the axial position. So we have these 1,3 diaxial interactions between the ethyl group and these protons where it's not present in the structure on the right. All right, so let's move on and let's talk about cis-trans isomerism for a couple of minutes. And we've seen compounds where we have groups that are on the same side of the ring, and then we've seen compounds that have groups that are on this opposite side of the ring. So when you're naming a cyclohexane, we use the prefix cis when two groups are on the same side of the molecule. And these are Haworth projections here. So this is a Haworth. Sometimes people pronounce it Haworth projection, but this is a Haworth projection. Okay, so if the two groups are on the same face of the ring, we say that they're cis. So this would be cis 1,2-dimethyl cyclohexane. If you're wondering how would I represent that in 3D, or sorry, in just a regular bond line structure, we draw it the way that it's kind of written here. So you would have it like this. Here's your cyclohexane. You'd have one methyl group going up, and you'd have the other methyl group going up like this. Whereas if you have one methyl group going up and one methyl group going down, then they're not on the same face of the ring. And so you would call that trans 1,2-dimethyl cyclohexane. These compounds, we call them stereoisomers. Stereoisomers. And chapter 5 is going to focus exclusively on stereoisomers. So chapter 5, something to look forward to. But what's a stereoisomer? It's a compound that has the same connectivity as another compound, but they cannot be interconverted by conformational change. If you put it another way, the arrangement of the atoms in space is different. They have a different spatial arrangement of atoms, meaning that even though the connectivity, like the way the atoms are connected here and here, are identical, I can't take this compound and overlap it on top of this one. It doesn't overlap, right? You see, the methyls that are both wedges work, but then I have a dash and a wedge, so they don't overlap perfectly. Okay, so those are called stereoisomers, and again, we're going to focus on that in chapter 5. But you need to know that when you have molecules that are cis and trans, we say that they're stereoisomers. They differ in the arrangement of the atoms in space. Now, if you're saying, well, this is all well and good if I just draw it in this way, but what if I look at a chair? You know, what does it look like then? Well, of course, each compound is going to exist as two equilibrating chairs. And when I have the cis compound, so here's the cis compound, meaning both of the methyl groups are on the same side of the ring. In both conformations, both chairs, you have one substituent axial and you have one substituent that's equatorial. Whereas if you look at the trans, you see something very different. In the trans, here are our substituents. We have a methyl group and we have the other methyl group, but now you've got one going up and one going down, meaning that they're both, or sorry, you have one that's axial and the other one being axial, up an axial and down an axial in the first conformation. But in the second one, you have one methyl group going up an equatorial and the other methyl group going down an equatorial. And so this conformer is going to be much more stable. So this is the lowest energy conformation. More stable because we don't have any of the 1,3 diaxial interactions, and we have a whole pile of them in here, right, between these hydrogens that are axial and the methyl groups that are axial. All right, so cis-trans stereoisomerism. Two groups that are on the same face of the molecule, we say they're cis to each other, and two groups that are on opposite faces of the molecule, we say that they are trans to each other. So cis and trans, very important. Everybody needs to know cis and trans stereoisomerism. Okay. Well, with all that in mind, I'll just show you that the last section, which deals with polycyclic systems, namely decalins, which are found in things like testosterone and cholesterol, and any kind of steroid. We don't cover this section. It's not covered on your final exam or the quiz or anything, but I would recommend taking a look at that if you want to. And it also talks about how bicyclic systems are found in all kinds of different natural products like camphor and camphene, which are really neat fragment compounds. And then it also talks about the structure of diamond, which is something that you would have seen in General Chemistry 1. But again, I won't be asking you any questions about section 4.15.